Muy buenas tardes, querida audiencia de la Cuarta Conferencia Espacial del Paraguay. Tengo el honor de presentarles al profesor Dr. Mike GRUNTMAN, quien es profesor en astronáutica, decano fundador del Departamento de Ingeniería Astronáutica de la Universidad del Sur de California, más conocido como de sus siglas en inglés USC, especialista en astronáutica, física espacial, sensores espaciales e instrumentación, misiones espaciales, cohetería, educación espacial, entre otros. Fue co-investigador principal y participó de varias misiones importantes de la NASA. Posee también más de 300 publicaciones académicas y 4 libros. Él hoy nos va a presentar acerca de la maestría en ingeniería espacial en la Universidad del Sur de California. Con ustedes, el profesor Dr. GRUNTMAN.
Hola, señoras y señores. Beta copia. I am Mike GRUNTMAN, Professor of Astronautics at the University of Southern California. First of all, let me thank the organizers of this space conference in Paraguay for inviting me to talk about the space engineering education. In particular, we will talk about a Master of Science degree in Astronautical Engineering. So I will start with the describing space engineering education in the United States. Then I will talk about astronautics at the University of Southern California, USC, a little bit about program statistics and distance education, which is very important, and then I will concentrate on the master's degree. So there are a number of publications about the program, and they can be downloaded from this website shown here. Just I also would like to introduce myself briefly. I'm a specialist in space science and technology in the various areas. I participate in several NASA space science missions, and I served the founding chairman of the Department of Astronautical Engineering at USC in the middle of 2000s, and I also served again a few years ago. So historically, in the 1930s, a number of aeronautical engineering departments was formed in the United States to support development of aviation. In late 1950s, when the space age began, these departments became the home for space engineering, for the space engineering education. And many departments changed their names to aerospace engineering departments or departments of aeronautics and astronautics. The number of the departments in the United States continuously grow, aerospace departments, and this growth continues until this day. Today, we have approximately 70 Bachelor of Science degrees in aerospace in the country and more than 60 Master of Science degrees. In the year 2000, we called for establishment of a separate, independent, pure space-focused Department of Space Engineering or Astronautical Engineering. And the driver was that a competition between pure space engineering departments, aeronautical engineering departments, and traditional aerospace departments would bring the desired mix of educational programs to serve the needs of space industry and the space enterprise. So in 2004, the University of Southern California established such a department, and we actually built it upon a specialization in space engineering that we created in about 1995. And this specialization was within the aerospace engineering department. Very quickly, we built up a new department that offers the full set of degrees in astronautical engineering, Bachelor of Science, Master of Science, PhD, and others. The Master of Science component became one of the largest in the country. So a few statistical numbers. Since the inception of the department, we awarded more than 160 Bachelor of Science degrees, and what is important, more than 650 degrees on the Master of Science level in astronautical engineering. This is a very large number. In fact, this constitutes about 3 to 3.5% of the number of master's degrees awarded in the United States in the much broader aerospace engineering field. National statistics does not distinguish between programs in aeronautical, astronautical, and aerospace engineering, so they're all together. And the space engineering is actually a smaller part of the large aerospace field, and so we account for approximately 3 to 3.5% of the degrees in this very broad field. The program continuously grows in terms of the degrees awarded to our students. So it shows that from 2004, from the inception of the department, we doubled the number of the awarded degrees annually. So this figure also shows that we award degrees to on-campus students studying full-time and to students who study part-time and work full-time in space industry. So, and approximately 1/2 of our degrees goes to the on-campus students, and 1/2 of the degrees goes to the students studying online. So 1/2 online. Now I want to say that online studies, distance education, became the way of life, in particularly in the space industry, in aerospace and defense industries. So the large companies hire, and government centers hire Bachelor of Science engineers, and they encourage them to study part-time while working full-time to achieve the master's degrees. So in our program, we have students who work full-time in all largest American legacy aerospace and defense companies such as Boeing, Northrop Grumman, Lockheed Martin, and others, and in many government centers. Now, what is important to maintain the quality of the online program? So we made sure that the degrees that are earned by our online students and on-campus students are identical. Everything is identical. The requirements, the admission criteria, the coursework, lectures, homework, exams, everything is identical. I also want to say that during this pandemic, there was an explosive growth of distant education, online education, and this took place across all the disciplines, not only in science and engineering. And because my School of Engineering was so heavily present in distance education since 1970s, so we actually handled this emergency very well. We expanded our programs, but distance education after this experience this year with the pandemic would play even a bigger role. So in the past, as I said, we started in 1970 in distance education. In the past, we relied on the television, so they shown antennas beaming our classes to geostationary satellites. So today it is internet based, so you don't rely on this television technology. And the quality of delivering courses and educational products continuously improves. It's actually very high already today, and during this year, because of this pandemic and the explosive growth of distance education, the quality of delivering would become even better and better. So now about our master's program. What are the admission requirements? Just first of all, this is a key feature and very important for space engineering education in particular, is that space industry, space technology includes exceptionally diverse areas of science and engineering. It's all flavors of engineering, also physics, mathematics, chemistry, astronomy, and others. And because of that, a number of specialists with varying educational backgrounds work in development and applications and use of space technology. And in order to advance their space-specific education, they need to get advanced degree as a Master of Science in Astronautical Engineering. So we specifically designed our program in such a way that we do not require a Bachelor of Science degree in aerospace engineering. So engineers with all kinds of degrees, undergraduate degrees, Bachelor of Science degrees, and Bachelor of Science degrees in science could come to our program, and we will take them from there. We also require a certain grade point average in the undergraduate studies and GRE's exams. So the coursework consists of 9 courses. 9 full semester long courses. We have 4 required courses in the 4 areas that we consider absolutely essential for anybody who works in space. And the first course is the spacecraft system design, basically an overview of the entire space system area. And the second course is in space environment, because the conditions where satellites operate in space are very different from what we have on the ground. It's a vacuum, radiation belt, solar wind, X-rays, and other things. Then spacecraft propulsion, which is basically rocketry, and orbital mechanics. Then the students choose 3 more core elective courses from a list of our highly specialized space courses. And in addition, they choose 2 technical elective courses that could be any graduate course in science and engineering. In reality, most of our students take these 2 elective courses from the list of core electives, because this is the list why they came to our program, because of the offering of all these specialized space courses. The thesis, the master's thesis, is not required, it is optional. Obviously, the distance students, online students, they cannot participate in hands-on activities. However, our on-campus students, which is 1/2 of our population, they engage in a number of the student projects, particularly building liquid rocket engines and other very interesting things. So the current coursework available to our students is very broad. It's probably, I would say, it's an unmatched selection of courses in various areas relevant to space technology. So I color-coded them. We have a cluster of courses that deal with the space systems. Then there are courses in orbital mechanics or spacecraft dynamics, you would say. It's orbital mechanics and attitude dynamics. There are a cluster of courses in propulsion. And in every cluster, there's an introductory course, for example, spacecraft propulsion, and then there are courses going deeper into this area, liquid rocket propulsion, solid rocket propulsion, advanced spacecraft propulsion, and so on. There are courses on structural dynamics of spacecraft, on the spacecraft subsystems, and then there is a couple areas that are growing now rapidly. One is the reliability and space safety, and another area is a human spaceflight, in particular in the United States. It's important because in addition to NASA that historically flew astronauts, today a number of private companies look for flying humans into space. And finally, a little bit about lessons learned. So first of all, the program should identify the customer and focus on that. Who are our potential students? They are working engineers in industry, government. They are students, upcoming students from the undergraduate studies. We also have to pay attention to feedback from our customer, from industry and government, and from students as well. The program identity is very important, to focus on a clearly defined area of technology, and actually prepackaging some courses in a cluster that students are advised to take helps students to understand, better understand their educational objectives, because very often students have very vague idea what they want to study. And again, as we already emphasized, we have to make sure that we can admit and educate students with a very diverse educational background, various areas of engineering and science, and we will take you from there and bring you into space engineering. In terms of administrative component, on the university level, administrative independence is very important, because when space engineering is part of a larger aerospace department, it's open to all kind of the internal university politics, and the university politics is known to be vicious and very unpleasant. So the program also needs to have a certain critical mass in terms of number of instructors involved and students. And also financial soundness is important. When a program is not a financial burden for the university, then it brings a lot of flexibility and opportunities to experiment and grow. Now, another word about another feature of distance education. The distance education provides a unique, unbiased quality check of the program. Now, think about this. There are practicing engineers who work in the large companies such as Boeing, Lockheed, or NASA centers, and they interact with their senior colleagues, peers, senior engineers, and they choose, these young engineers choose which online program to take to get a master's degree, and they have a tremendous choice in the United States. So, and by the way, the distance education doesn't have borders, so now you can just take courses in other countries. So these engineers have choice, and if they choose a certain program, that means that brings a specific practical, real value, educational value to them, to advance their professional careers, to grow professionally, and to become a more advanced specialist and work in advanced areas. So if a program grows, then it's an indication in a competitive environment. It is an indication that the program provides something of value and it is a program of quality. So our program, as we discussed a few minutes ago, had been growing since its inception and actually doubled in size. So our customer, our students, do value what they get. And finally, the world enterprise, $420 billion today. It's a government and commercial, is very diverse in many countries and programs. Large and small, sophisticated and not that sophisticated, contribute to advancement and applications of space technology. We explore the solar system and reach to the stars, and at the same time applications of space technology such as remote sensing, communication, global positioning system make differences in lives of people, improve efficiency of governance, and bring prosperity. And the space education, space engineering education is a foundation for advancement in this field, and the space engineering education will continue to grow. Ad Astra, to the stars, saludos.
Muy buenas tardes, querida audiencia de la Cuarta Conferencia Espacial del Paraguay. Tengo el honor de presentarles a Todd BARBER, quien es un ingeniero de propulsión de la JPL, del Laboratorio de Propulsión de Jet de la NASA, que trabajó en la misión Cassini a Saturno y la misión Mars Exploration Rover. El ingeniero BARBER también trabajó en la misión Deep Space One, la primera misión de la NASA en utilizar un motor de iones, los mismos motores que ustedes ven en la película de Star Trek, para propulsión primaria. Todd BARBER trabajó en el proyecto Galileo durante más de 7 años. También trabajó a tiempo parcial en la misión Space Infrared Telescope Facility, o el SIRTF, y en la misión Stardust, así como en la misión Mars Sample Return. Todd recibió el premio al logro excepcional de la NASA en 1996 por su trabajo en Galileo. El ingeniero BARBER es nativo de Wichita, Kansas. Estudió en el MIT entre 1984 y 1990, obteniendo su grado y maestría en ingeniería aeroespacial. Aquí nos hablará de la misión de la NASA Mars 2020 Perseverance. Con ustedes, Todd BARBER.
Buenos dias. My name is Todd Barber with NASA's Jet Propulsion Laboratory, and I am delighted to participate in this conference, a virtual conference from Paraguay. And Dr. Kurita asked me to speak about the Mars Perseverance rover, NASA's latest mission to the Red Planet. And I'm delighted to do so today. I am the lead propulsion engineer for operations of this rover. Now, of course, the rover itself has no propulsion system, so my job is basically to get it from Earth to Mars in a short 6.5-month cruise. We launched July 30th of 2020, and landing is all set for the afternoon of February 18th, 2021, a Thursday, and wish us luck with this exciting landing. And today I would love to tell you about the mission, what we hope to learn, some of the challenges along the way, and the excitement of trying to build, test, and fly a rover all during a global pandemic. And if this isn't a challenging enough undertaking, even during good times, COVID-19 has made it especially difficult. But throughout that, we are confident and hopeful for a successful landing to kick off 2021. So this is an artist's conception we're seeing right now of Perseverance rover. All of our NASA rovers have had naming contests by students kindergarten through 12th grade, all pre-college students in the United States that submit essay contests to see who gets the right to name our rovers. Our first rover was the tiny, cute Sojourner rover, named after the American abolitionist Sojourner Truth. And this rover was about the size of a microwave oven or child's wagon. That was clear back in 1997. Then in 2003 and 2004, we built and launched the Mars Exploration Rovers, MER rovers, Spirit and Opportunity. And those were named by a young orphan from Russia named Sophie Collis. And she said, as a young child in Russia, I dreamed of moving to America, land of opportunity. And my spirit kept me going. And so we loved her essay. And that's how Spirit and Opportunity were born. 2 golf cart sized rovers that were supposed to last 3 months on the Martian surface and ended up going for 6 years for Spirit and 14.5 years for Opportunity. We also had the Mars rover Curiosity in 2011-2012. That was named by Clara Ma, a young student from my home state of Kansas in the United States. And I'm proud to say she has ended up working in the aerospace field and it was inspired by that as a young 12-year-old girl. To name the Curiosity rover, which, by the way, is still exploring the Red Planet. It is 8 years and counting into its 2-year mission. Finally, though, onto this rover, a big, bad rover named Perseverance, and boy, was that a perfect name for a rover that was attempted to be completed and launched in the year 2020, dealing with a global pandemic. There's a young boy from Virginia that named the rover, and we just had no idea how perfect that name would end up being. A spoiler alert, this rover also carries a little passenger, a drone helicopter called Ingenuity, and that was also a name selected by a high school student in Arizona from the United States. So that's a beautiful shot of the rover. Let's talk about this mission. Next slide, please. So we at NASA have had a long, beautiful history of going to the Red Planet. And this is the missions just since the new millennium started. A series of orbiters, landers, and rovers. And I'll walk through these. Every 26 months, Earth and Mars line up so that a Hohmann transfer ellipse, a minimum energy trip to Mars, if you will, can occur. And that's why if you miss a launch, you have to wait 2 years, 2 months. So we really are under pressure to make these launch windows. A Hohmann transfer ellipse, by the way, is an ellipse, a half of an ellipse, an oval-shaped orbit that is tangent to Earth's orbit on the inside and Mars' orbit on the outside. So looking through this, in the lower left are the landed missions, and in the upper right are the orbital missions. And I'll start with the orbiters first. Mars Odyssey launched in 2001, and amazingly still talking to that mission. It's unbelievable. And it serves as a relay satellite for our rovers and landers to help get more data back. It also provides crucial data during entry, descent, and landing, or EDL, during the critical events when our landers or rovers arrive at Mars. We had Mars Express, a European mission, so it's still working as well, launched in 2003. Mars Reconnaissance Orbiter has 0.3 meter resolution cameras. We can see something a third of a meter across on the Mars surface. If there were Martians playing beach volleyball, we could see the we could almost resolve the volleyball. We haven't seen that yet. We'd let you know. But that mission is going as well. Then MAVEN is a Mars orbiter that is sampling the upper Mars atmosphere. That's still doing its work too. And then the Exomars Rover, another European mission. So we have a whole flotilla of international missions at the Red Planet right now. Now going to our rovers, starting with the Mars Exploration Rover, that's Spirit and Opportunity, launched in 2003, landed in January of 2004. I mentioned that mission already. We had a couple of failures of Mars missions in the late 90s. We reflew an attempt to land near one of the poles of Mars, and that's Phoenix in 2007. So that landed in May of 2008 and lasted some months, although the weather conditions near the poles are much more harsh than near the equator. So that mission didn't last, for Mars years as other rovers have by design. So we found water ice underneath the first few tens of centimeters of Martian soil. So that was an exciting mission. We found salt as well. We didn't find tequila. Our comedians in the United States said we were looking for tequila to build a margarita on Mars. Not true, but we were 2/3 of the way there with the water, ice, and the salt. On to 2011, we have the Curiosity Rover. This is a mission that landed at August 5th of 2012 for a 2 Earth year mission, a 1 Mars year mission. And as I mentioned, we're still going 8 years and counting, going strong with the Curiosity Rover, exploring the peaks and valleys of Mount Sharp on Mars within Gale Crater. And these have clay deposits, sulfate deposits. It's a liquid water former environment on Mars. On to 2018, we have the Fixed InSight lander, another NASA JPL mission. And this is a fixed mission, but it's measuring Mars quakes, seismic activity on Mars to determine the deep structure. We also have a burrowing mole that we're trying to figure out how to get to go down to about 5 meters depth to take Mars' internal temperature. And that helps us understand the interior properties of Mars as well. And we have measured Mars earthquakes. That's very exciting. It allows us to map the interior. The Exomars Rover is a European mission. Unfortunately, due to some delays, including some COVID-19 concerns, they were unable to launch in this opportunity window. And that's happened to the best of us. Curiosity Rover was supposed to launch in 2009. We had to wait till 2011. So the Europeans will try 2022 when Earth and Mars line up. And then finally, at the lower right is the Mars 2020 rover, now named Perseverance. It's quite amazing to see these flotilla of spacecraft all heading to the Red Planet. Now, I should mention, this is a good chance to mention, even though ExoMars wasn't able to make the brief launch window in 2020, there is an international coalition heading to the Red Planet at this time. The Chinese launched a Mars orbiter, lander, and rover during this Mars opportunity as well. It was about a week before we launched Perseverance, and they're en route to Mars and doing well. They've done their first maneuvers. Very excitingly as well, the United Arab Emirates, UAE, have launched their first interplanetary mission, a Mars orbiter called, I believe it's called Hope, and it's on the way. and doing well. So we're very excited to welcome the international community into this opportunity to get to the red planet. Next slide, please. So as mentioned on the title slide of the last page and this one too, Mars is a cold, dry desert now, like the Antarctica on Earth, but in the billions of years history of the solar system, it definitely had liquid water. We can see that from the chemicals, the rocks that were left behind, the mineralogy. We see it in terms of dried riverbeds and lake beds and dried flow channels that could have only occurred with liquid water. Today, the liquid water is not on the surface. It can't be supported with Mars' thin carbon dioxide atmosphere and cold temperatures. You might have some water ice in spots, and we know that does exist, although it does tend to sublimate. In other words, change straight from a solid to a gas in the Mars atmospheric conditions. So it's tough to say whether Mars ever had life or if it has life today. It's difficult to think of it having life on the surface today because of the lack of liquid water, a lack of the ultraviolet light from the sun is not good for organic molecules. However, we think there's subsurface liquid water on Mars today. If life ever existed, maybe it followed that water underground. And the real key is just to understand, was Mars ever habitable? Did life start there billions of years ago? In some sense, it was a better place for life to start than Earth a few billion years ago, because the Earth was warmer, the sun was putting out more output. Also, Earth has more gravity, so it was more of a target for comets and asteroids to come in and wipe out life, even if it got started. Mars was a smaller target. So given that it had a favorable atmosphere, liquid water, and was less of a target and further from the sun, it suggests Mars was even a more friendly place for life to have formed billions of years ago. So that's what the Perseverance mission will do. We're going to aim for an environment that could have definitely been habitable. It had all the basic building blocks of life. Some are still there today, and we're going to a place that in Mars history would have been a perfect place for life to start. Next slide, please. So that, of course, drives what we do. Now, we've had missions before, including the Viking landers and orbiters back in the mid-1970s, and that was go for the home run. You know, scoop up some soil, basically look for life on Mars. And, you know, how do you know life when you see it? Well, it's tough. It's a tough question to answer. You know, if it eats, breathes, reproduces, poops, moves, you know, it could be life. So we took the soil and fed it nutrients and did chemical experiments, and all of those experiments came up negative for life in the Viking days. One experiment did have a chemical release that was very interesting, and the principal investigator claimed they found life. But of course, the great Carl Sagan said extraordinary claims require extraordinary evidence. And it turns out we think there's weird peroxide chemistry going on in the soil that tricked that detector into making chemical releases that emulated some biology. But we don't believe we detected life there with Viking. However, see, instruments and sensitivities have improved so much since Viking. We are much better equipped now to read the rocks to see if life ever formed on Mars. We're generally not looking for extant living organisms with the Perseverance payload, but we're landing in a place that had liquid water. We have very sensitive measurement techniques, and we'll be able to more positively determine if this place ever had life. And to that end, for the first time ever, we're also going to collect samples, store them in hermetically sealed tubes for a future to be funded and designed Mars sample return mission. Actually, the design is almost there. And this is just a first necessary step to collect the samples. And I'll talk about that further as we go on in the presentation. But NASA has long wanted a campaign to return Mars samples to Earth so we can examine those rocks and soil particles to see, did life ever exist on Mars? And a first step is to collect the rocks and dirt. Next slide, please. So we picked a landing site that should be very favorable for past life on Mars, as I mentioned, and reading the rocks is the key to see what the possibility of life was. And we're going to find the best sample. We have dozens of test tubes that we'll store with these samples and seal the test tubes up. We'll drop those test tubes on the Martian surface for a future rover, a fetch rover, to go get them, and then somehow get them to a MAV, a Mars Ascent Vehicle, that would then blast them off into Mars orbit. It would rendezvous with a to-be-built Mars orbiter that would retrieve the samples about the size of a basketball containing all of those test tubes. And then we would have to inject that orbiter on a trajectory back to the Earth. It would come back and intersect Earth's orbit, probably do an Earth orbit capture. Then somehow we got to figure out how to bring the samples from Earth orbit back to the Earth and then not contaminate the Earth, a la, the Andromeda strain, reverse planetary protection. So we're not only worried about, we don't want to contaminate Mars with Earth life. We definitely don't want to bring back any potential Martian life and have it cause another pandemic here on Earth. COVID-19 is enough. So this is an exciting part of the Perseverance mission, is to begin the grand journey of the first sample return from another planet. Next slide, please. Okay, so these rock samples, there we can see some of the test tubes, and the honeycomb-looking structure is how they're stored on the Mars vehicle for later drop-off. And you can actually read the rocks. We can dig them in. We can give very small portions to researchers around the entire planet Earth, and all the best labs on Earth can take to the task of understanding and investigating these rocks, things we couldn't do on the Martian surface, where we have limited mass, power, and volume to take scientific instruments. So that's the key of a Mars sample return, is to get these back and basically give it to as many researchers as possible for detailed study. Next slide, please. Okay, so we're not looking straight for life, but there's something called a biosignature. And what we see in Earth, any place where biology has been prevalent, it leaves traces of itself in the rocks, objects, substances, patterns. And, again, Occam's razor, the simplest explanation is probably right. So if you can explain it away without using biology, then that's probably the case. Extraordinary claims require extraordinary evidence. But we definitely find things on Earth that Occam's razor would tell you, well, as crazy as it's not so crazy on Earth. We know life is abundant here. But we can say that definitely was formed by biology. So on Mars, if we see these similar kinds of things, that would be an incredible clue that life started independently on the red planet. And that drives a lot of what we do at NASA JPL. Next slide, please. So once you've decided to go there, we have to pick a landing site. And that's a fun job in and of itself. The journey to Mars is over 500 million kilometers, yet we can land in an ellipse, an oval that's only a few kilometers wide by a few kilometers tall. And that's due to excellent interplanetary navigation and control, and then actually a smart landing system that is terrain mapping and flying to a given location. What we've done well through the decades is to shrink that landing ellipse, because the scientists and engineer have very different goals. They're at odds with each other, frankly. The scientists want to land, next to very sexy, exciting craters and giant canyons and rappel down cliffs and all these things that give engineers heart attacks, because engineers want to land in the most flat, boring plane they can find. Unfortunately, those planes tend to be scientifically rather uninteresting. So as you shrink the size of the landing ellipse, you're able to more effectively target science-rich areas that are yet safe for the engineers. And some of the engineering constraints, it has to be a place that's low on Mars, low elevation, so the atmosphere has enough time to slow you down. And there can't be too many crazy big rocks, and the slopes can't be too big. It also has to, depending on the mission, be fairly near the equator. We're not solar powered here, That's the good news. But if you get away from the equator, it just gets so cold, it's really hard to survive. So this is our 3 sigma landing ellipse for Perseverance in Jezero crater, and I think in Sidus Planium or something. And this is 3 sigma means 99.8% of the time I'm going to guarantee I land within that black oval there. And what's really interesting about the black oval, to the upper left there is this fan-looking material. That is an ancient river delta on Mars, like the Mississippi River Delta or the Amazon River Delta in South America. So this is a place where water flowed out into a lake or ocean, sediments deposited. So this is a former liquid water environment on Mars. And what a perfect place to land to look for signs of ancient habitability and life. And we will go exploring well outside of that black ellipse as we drive the Perseverance rover. Very exciting place to land. Next slide, please. So there it is, the ancient river delta. And some of these rocks are ancient. They formed very early in Mars history. And that's when the atmosphere was thicker and liquid water flowed. So that's what's so exciting. But doesn't that look like a river delta on Earth? It's a really cool place to land. The view should be spectacular and the science should be just unbelievable, assuming we can safely land on the surface. So stay tuned for February 18th of 2021. Next slide, please. So what we see from orbit, we can see rocks and minerals from our spectrometers, from orbiters, and we see minerals that only form in liquid water. So as if the appearance is not enough, we need better evidence than that, chemical evidence. And we have it from orbit that this place has rocks that only could have formed in liquid water. Moreover, a lot of those are commonly associated with Earth life. So this is a place that's very high on the habitability scale in ancient Mars history. So this shows an example traverse. If we happen to land in the center of the ellipse, we might drive up, towards that rock face, start exploring this ancient river, the direction that the delta came from, and the deposits. It's going to be a wonderful off-roading adventure on Mars. So stay tuned for that. Very exciting. Next slide, please. Okay, the rover itself is a 6-wheel rocker bogie suspension design, about the size of an SUV, a sport utility vehicle. So this is a big, bad rover. Mars 2020 Perseverance looks a lot like MSL. To the, at first glance, it's like WALL-E on steroids, if you're familiar with the WALL-E movie. This is a huge, big rover ready to go do some exploring. Has similar science payloads, but there's some differences. I like to point out about 4 differences, and even before I go to the next slide, I'll mention those. Number 1, and I'll cover this in more detail on the slides. Number 1, we have the caching, C-A-C-H-I-N-G, sample storing capability in these test tubes for a future Mars sample return mission. That is something completely new for Perseverance versus Curiosity. Number 2, we're going to make oxygen out of the Mars carbon dioxide atmosphere, so Matt Damon and others can breathe there in the 2030s. And this is very exciting. We're only making about 1 gram per hour, and we're not going to store the oxygen, but it's a technology demonstration, a proof of concept to make sure that we could eventually form oxygen out of Mars' thin carbon dioxide atmosphere. And oxygen would be so useful for future missions. Could be used as an oxidizer then in a Mars sample return rocket as the oxidizer. We could use the oxygen for astronauts to breathe. There's lots of uses for that. So hopefully this instrument called MOXIE will do its trick on Mars. Number 3, we have 2 Mars microphones on this Perseverance rover. That's very exciting. We'll be able to hear the sounds of Mars, the winds, the gears grinding, the vehicle moving, doing science. Now, the only trick is we've launched Mars microphones twice before to Mars. Both missions have failed, which leads to the question, what don't the Martians want us to hear? I just don't know, but hopefully 3rd time's the charm, we'll get the Mars microphones working. And when we think about it, how beautiful. It's a way for our visually impaired taxpayers and citizen scientists to come along the rich journey of planetary science as well. They're able to experience Mars in a new and different way. It's very exciting. And fourth of all, the fourth difference from Curiosity, and maybe most sexy, we have this drone or helicopter that rides under the belly of the rover. We'll drop it down and it will do little flights on Mars. And what a challenge to have the first aerodynamic aerial vehicle on the surface of another planet. And that is also a technology demonstration mission. It doesn't necessarily have its own science mission. We want it proof of concept. Does it work? And if it ends up working, we'll likely baseline it for future missions. So having said that, next slide, please. We'll probably start to see some of the details. First off, if you go someplace scenic, bring your camera, and we're bringing 23 of them on this Mars rover. We have super cams. We can actually do microscopic imaging at a distance. That's amazing. Zoom lens. Mast cams, the mast is the neck of the rover. Nav cams are navigation cameras to help us with driving. We have cameras on Sherlock and Pixel. Those are the science instruments out on the turret at the end of the robotic arm. We have hazard avoidance cameras called HazCams, rear and front HazCams. There's other engineering cameras, science cameras, and there's cameras for EDL itself, entry, descent, landing. I think we have one looking down like we had for Curiosity. I think we also have one pointing up, which is something new. So we're really tricked out with a lot of wonderful cameras on this rover. Next slide, please. So this is the science instruments to, we can look near and far away, large objects, small objects. And since we have a stereo pair of mass cam images, we can do stereo imaging. And with a pair of 3D glasses on Earth, we can sit and feel like we're on the Martian surface. You can do that today. Google Mars 3D and get a pair of those glasses, and you can see what our other rovers and landers have seen in 3D, along with our orbiters looking down. They do stereo imaging as well, just from moving along in their orbit. We also have SuperCam. This can fire a laser up to about 10 meters away and vaporize rock. The gas cloud coming off the rock can then be analyzed with spectrometers to determine what the rock is made of. So we had one of these on Curiosity as well. And the question the young students always ask is, would this laser hurt you if you got in the way of it? So I found the person that built it and asked them, and they looked me up and down, dumbfounded, and they said, well, it can vaporize rock from 10 meters away. What do you think, Einstein? So yes, that was silly of me. Of course it would hurt you if it can vaporize rock. So we come in peace, tell the Martians we mean no harm, but we are armed with a Martian death ray, and we will use it if attacked. Next slide, please. So here's the microphone. We are a good listener, a couple microphones, and we finally, hopefully, hear the sound of Mars. One is on the side of the rover there. The other is up towards the face of the rover on the mast. And we're excited to hear the sounds of the red planet for the first time. Next slide, please. Okay, we've got a couple meter long robotic arm. We can scoop, drill, study rocks. And there it's actually doing its curls. It's doing its weightlifting. We're testing it out in our bunny suits. This is in the JPL Taipei 1 SAF, Spacecraft Assembly Facility, our clean room facility. These clean rooms are quite interesting. They are kept super clean. There's HEPA filters. An average air molecule will spend 3 or 4 minutes in the room. We have a slight positive pressure in the room. So every time you open a door, clean air rushes out rather than dirty air rushing in. And that's the opposite of what we do in like the Centers for Disease Control in Atlanta. You don't want to kill all the nice people in Georgia and the United States. So we have a negative pressure in the room. Every time the door opens, the air rushes in. And you have to take an air shower and get in the bunny suit and get your feet scrubbed, electrically grounded, because the cosmetics, hair, skin flakes, all these things can damage our delicate rovers and other spacecraft. Next slide, please. So we have Sherlock and Pixel are on the robotic arm. These are 2 rock analyzers, and we can look at tiny, tiny areas. We can do mineralogy. It's like having a robotic geochemist and a geologist on Mars both. We can look at what atoms are there, what minerals are there, whether they're hydrated or not, figure out what the pH was when the liquid water was there. We can look at different isotopic ratios to determine the age of the surface. With lighter elements, they tend to disappear, the lighter isotopes of that. So we look at the ratio of those isotopes. Very exciting scientific complementary payload to read the rocks of Mars and determine its ancient history. Next slide, please. So in the belly, this is the dozens and dozens of test tubes. I've had a friend that spent 5 years of his life just figuring out how to make those test tubes seal. So incredible effort to start this Mars sample return campaign. And we'll store and preserve these pristine rock and soil samples. The rover will be smart enough and will drive it and control it from Earth to figure out what are the best samples to store in these test tubes for a future mission for pickup. Next slide, please. So here is MOXIE. MOXIE breaks down the CO2, carbon dioxide, in Mars' thin atmosphere, and through a chemical process that's been around since the 1800s. And we do it in an efficient way to extract the oxygen out, the O2. And so in a sense, that's what trees do, right? Photosynthesis takes in carbon dioxide and releases oxygen. So it's like having a mechanical tree on Mars to produce O2 in a technology demonstration experiment. Next slide, please. And as I mentioned, this maybe the public gets most excited about Ingenuity, our Mars helicopter, first robotic flight on Mars. So if you imagine the challenge, this is like trying to fly at 30,000 meters, 30 kilometers on Earth. Think how thin the atmosphere is, because Mars has 1% the surface pressure that the Earth does. So the beauty is, from past orbiters and landers, we know what the Mars atmosphere is like. You know, the density, the carbon dioxide composition, the temperature, pressure. So with those, with that knowledge, we can go do and figure out what would it take for a Mars helicopter to fly. Well, it better be lightweight, because even in Mars 3/8 gravity, there's just going to be so little lift in such a thin atmosphere. So you need rapidly rotating, long, thin blades. We have that. That's the key to get the aerodynamics to work. And the vehicle's very lightweight. It does have a camera. It can look down on the surface, do little short hop flights, take photos of the rover. So it's not going to follow the rover for very long. It's only about a 1-month mission. So the rover will be hanging around where it landed for the most part. Those two will buddy it up for the first month, but then the rover will continue its adventures. And hopefully the helicopter will work well. Now, we can design it, and that's great evidence it'll probably work, but it'd be great to test it. So we actually tested it on Earth. We put it in a vacuum chamber, simulated Mars carbon dioxide, thin, cold atmosphere, and took it for some test flights, and it worked well. So that gives us more confidence that it will likely work well on the red planet. Next slide, please. We put it, this is the rover upside down. You can see the blades of the helicopter, the panels up top. And so we'll flip the rover over with the helicopter underneath, drop it down, drive the rover away, and then the helicopter is ready for some test flights. Next slide, please. This is interesting. RIMFAX is a radar that can penetrate the surface. So I don't think it goes very far down. I'm not sure how far down, but we can see differences of sand, rock, and ice. And this is exciting to read the subsurface of Mars, because that's where some of the action will be, you know, as far as different materials, and to think about if life ever existed, and where's the ice today, and is there liquid water, things like that. I don't think we'll get down to a liquid water layer with RIMFAX, but it's exciting just to be able to probe the subsurface using radar. Next slide, please. So our launch window did open the 17th of July. We had some launch delays due to technical issues. frankly, we had some COVID delays too, some things where, you know, Kennedy Space Center in Florida would have to, they would see a case and have to stand down a few days. We finally did get launched on July 30th of 2020. So a couple weeks into our launch window, and we're well on our way to Mars now, over a quarter of the way there. February 18th, again, 2021 is our landing date. Next slide, please. Okay, on this slide, the spacecraft we see, I'll translate the 354 million miles as over 500 million kilometers, and this occurs over a cruise time of 6.5 months. So if you work out that mathematics, that ends up being a couple million kilometers a day, which is amazing. Couple round trips to and from the moon every day in our journey to Mars. And what we see, we approach Mars pretty quickly, and we actually accelerate over 21,000 kilometers per hour. Mars gravity draws us in ever faster. And what we see in this view on the left is the cruise stage with the thrusters hanging out. That's the vehicle that ferries the payload, and the payload is on the right. That includes the back shell, the heat shield. Inside that is the rover itself, along with the descent stage, a rocket-powered jetpack that sits on top of the rover to get it safely to the surface. Next slide, please. So compared to Curiosity, we've got some new smart landing capabilities here. We're going to take pictures on the way down, and we know from orbit what the map looks like, a terrain map. And if it looks like a scary place to land, it's actually going to change by firing the thrusters a little differently, divert to a little bit different landing site. And that's one way we get this landing ellipse so small and allow such a precision targeted landing. And that's good, because this is a more difficult place to land. There's rocks and hills nearby. Because it's scientifically interesting, it's also a little more treacherous. So this is the excitement of Perseverance, is to use some of this new autonomy. Now, by the way, we can't control this from Earth, because the signal moving from Mars to Earth is, I don't know exact one-way light time, but it's probably on the order of 10 to 14 minutes. Whereas the time from the top of the atmosphere to the surface is only 7 minutes. That's why we call it the 7 minutes of terror. So the vehicle has to do all of this by itself with no control from the Earth, given that pesky speed of light delay. It's the law, 300,000 kilometers per second. If you have a problem, take it up with Dr. Einstein. Next slide, please. So this is a Curiosity picture, but it's going to be very similar for Perseverance. When we're near the surface, the rover is lowered down on cables. We hover, killing our vertical velocity to 0, and then we end up laying the rover more gently than you lay a baby down in a crib, just a couple of meters per second, or less than a meter per second, if everything works. And the rover has radar on board that bounces off the Mars surface to tell how far away the surface is. And that helps those control algorithms when this part is called the sky crane, and it's just the last 20 meters of the landing. So hopefully it will work well. Next slide, please. Yeah, 2 miles per hour touchdown speed, so 3 kilometers per hour. Very gentle. And that's what we need to make the rover work. We then cut the cables, the descent stage flies away, 0.5 kilometer or so, crash lands, it's out of the way, and the rover's ready to go to do its Mars science mission. Next slide, please. So a Mars year is about 685 days or so, which is roughly 2 Earth years. And that's the prime mission here. Now, given Sojourner lasted 3 months into its 1-month mission, Spirit and Opportunity lasted 6 years and 14.5 years into its 3-month mission, respectively. And Curiosity is still going 8 years into its 2-year mission. This bodes well that we will have this rover going for more than 1 Martian year or more than 2 Earth years. And I imagine we will just have scratched the surface with the tremendous science opportunities that await us in Jezero Crater. Next slide, please. So this, again, is a part of a big campaign. We found a diverse landing site that's fantastic. It was an ancient liquid water environment on Mars. So because of that, we're going to explore its diversity, look for signs of ancient life, you know, more than just habitability. If we can get these rock samples, bring them back to Earth, maybe they will conclude that Mars had life at one point. And of course, the whole sample campaign return is a huge part of this. And with generating oxygen and checking the environment for habitability, we're really paving the way for future human exploration to the red planet. So this is the next natural step, most capable science instruments ever sent to the red planet. We are so excited to be on the way there, and stay tuned for February. Next slide, please. We are ready to roll, and of course, this is an old slideshow. We are actually en route. We're doing our trajectory correction maneuvers to fine-tune the Mars trajectory. We've, you know, flight has not been without its challenges. We've gone into safing mode 3 times in the first 16 days of the mission, which saving is your friend, but it means there were little issues to be worked. We're solving all these problems. It has not been a trouble-free cruise. We were just asking for it, naming it Mars 2020 and launching it during the year 2020. But I'm happy to say we're on course, looking great. We're solving these anomalies, and things look really promising for our February landing. Our website is mars.nasa.gov/Mars2020. And if you want a more direct link to the NASA site, just and more general Mars information, go to www.nasa.gov/Mars. And next slide, please. That is it. Thank you very much for your attention. And go Perseverance, go Ingenuity.
Thank you.
No, just thank you very much for muchas gracias. And really enjoyed talking about Perseverance mission. And I wish you a wonderful rest of your conference. Have a great time. And we'll see. I'm looking forward to seeing Paraguay having space successes in the future too. It's so exciting.
Yes, definitely. I stopped sharing the screen. I just wanna, you know, you don't need to share your screen, Todd, but I just wanna say, you know, look into, you know, our old face, so friend of you, don't forget about me.
Yes. Thank you for doing that. Since I'm not camera ready, but I really appreciate seeing you. And, Zoom is amazing. Here we're half a world apart, and delighted to share Perseverance's story with your conference.
Thank you.
And it was fun hosting your JPL tour as well. I'm glad you were able to see the lab when you came.
Oh, wow. I still remember that. I had the pictures, you know. You were showing me you were pointing me I think there was a heat shield that was back then, was there. And everything else was about to be, you know, assembled in the coming months. It was really exciting. I mean, and I saw the picture of the rover. I mean, the helicopter. It was the picture back then was just a picture. But it was very interesting, exciting. I mean, it's really, you know, for the youth and the young kids like me. I'm looking forward to experience this, you know, this event next year. Next year,
yeah,
very around the corner, right? I mean,
no, it's. I tell people, because I worked Cassini and Galileo, and those had 6 or 7 years out to the giant planets. Mars missions feel like instant payoff because you launch and then 6 months later you land. So you blink and it's over, and that's very exciting in this biz to have such quick payoff. You know, I don't work the 10 years before, you know, to all the hard work that goes into making the mission successful.
Thank you again, Todd. Really appreciate this time.
De nada. And I'm really glad to do that. And congratulations and good luck with your conference too.
Thank you. We'll be in touch with you again. Thank you, Todd.
Sounds great. Okay. Take care. Thank you.
Bye-bye.
Bye-bye.